Hi everyone. So the next thing we're going to do in the course is we're going to learn about math and then primitives. Now, you have taken linear algebra before, but I expect that many of you will have forgotten much of your linear algebra. And even if you don't really forget it, you might not understand what it has to do with graphics. So we're going to do a quick review to go over that, and hopefully add some. One thing I try to do in this section is to add some intuition to linear algebra. So you've learned linear algebra, but what does it mean geometrically and how can you use it in graphics? I'm going to focus on that. So today, linear algebra review. Is basically what we're doing. Okay. So of course, we all know what a point is, but I'm going to spell it out anyway because it's important, and you'll see why. It's a location in a coordinate system relative to the origin. So, no surprises here. Here's my coordinate system. Here's my origin down here. I have a point up here, and I'll call it x comma y. Easy, right? No big deal. Now that's my point. Yes, that's my point. Vector, on the other hand, is a directional quantity. So it's a direction. Which includes a magnitude as well. So magnitude, and direction. So that's a vector. And you can place it into a coordinate system. You can place it on a coordinate diagram. So it can be placed in a coordinate system relative to some point. Typically, maybe the origin is one common point. So I'm going to go back to my diagram here, and I'm going to add a blue vector. Right? I'll put a vector here. This is some other x, y, and usually you see them drawn like this to show that it's a direction relative to the origin. Now, of course, this vector can be drawn elsewhere, but we're going to come back to that, because a big point of confusion that strikes many people is this idea of a point versus a vector. People get these intermixed, and if you do anything advanced with vectors, you're going to make this mistake. They look kind of similar, right? They look kind of similar. There's an x, there's a y, but they're not the same thing, and they're not interchangeable. Okay, they're not the same thing. Let's draw. I'm going to draw another coordinate system here. Now, if I draw the following, I'll call that A, and I draw. Now I'm telling you that all three of these vectors, these are the same vectors, same direction, same length, same magnitude. So vector A is equal to vector B, which is equal to vector C, and they're the same. Same vector. Now, if I look at just the points that we have drawn them here, now the way I've drawn these vectors, it's just arbitrary. They're just directions. I can draw them anywhere in the coordinate system that I want. They will be the exact same vector. It doesn't matter where I draw them. But if I draw the points, that's not what I intended. If I draw the points here, those red points, A, B, and C, you can see they're very different points. A does not equal B and certainly doesn't equal C. These are different points, right? So it's pretty simple, really. A vector, even though it might have the same number, 3, 4, whatever, 3, 4 being a direction versus 3, 4 being a point are very different. Vectors and points, to make things worse, they're written down the same. They're often specified in matrix notation. So they're typically written like this, with the x on the top and the y on the bottom, and that just makes the multiplication easier because you post multiply with a matrix, but we'll learn a lot about that later. We typically write the 2x1 matrix. Remember, for matrices, you count down first and sideways. You can also do them the other way, but I will say that much more common in graphics. It doesn't really matter, it's the same value at the end of the day. Okay. So far, hopefully this is pretty straightforward. Just watch out with this idea of a vector, which is a direction, not being a point, which is a location, okay? There's a lot of problems that get caused by applying operations, assuming something's a vector when it's not, or vice versa. So let's learn a little bit about operations on vectors. Operations. So first, let's say I have a vector v. I'm going to draw it like that. That, by the way, is an arrow on the top. It's nothing fancy. And I'm going to give it a value of 1, 2. No big deal. Now, I can take a vector, and I can multiply that by a scalar. Remember, a scalar is just a standalone number. I'm going to get a vector, right? So I can work through that. It's easy. If I take v times 4, by the way, it's the same as 4 times v, right? It's going to be equals to each component times by the scalar. So 1 times 4, and then 2 times 4. So you're going to have each component multiplied here. It's going to be the same. This is going to end up being 4, 8. So no big deal. A vector plus scalar is also a vector. And it's lucky for us, it's just as simple. So if I take v and I add 5 to it, again, it's the same as 5 plus v is going to be 1, which is my x coordinate from above, plus my new 5, 2, 5 is going to be 6, 7. Okay, so you can just add it. No big deal. If I add a point plus a vector, wait a minute, you say, they look the same, right? X, Y, X, Y. If I add them together, I'm actually going to get a point. Because I have a point, I add some direction, I add some magnitude to it in a certain direction, and I find another point. Again, this is pretty straightforward. If I draw the coordinate system, I can imagine drawing a point 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So let's say I have my v plus 2, 2. Okay, so my v, remember, is 1, 2. 1, oops, that's an eraser. My v is 1, 1, 2. So my v is right there. That's a point. That's a vector, rather. That's where I am. Now the point I'm starting at is 2, 2. So 1, 2, 1, 2 is actually over here. And then if I add my vector of x of 1 and y of 2 to it, I get up there, like that. And that's my new point. So I start at the old point, I add the vector to it, and I end at the new point. And I actually drew in the vector at the origin there to show you the vector doesn't belong at any location until you add it to something. So if I do that, I just add them together, and this is 1, 2 plus 2, 2. This is going to give me a new point of 2, 3, 4, which is 1, 2, 3, 1, 2, 3, which works out. Great. It's always nice when it works out. Okay. 3, 4. Sorry, I paused there because there's a mistake in my notes, but my version here is correct. So that's okay. So point plus a vector is a point. Now, another operation you'll do a lot of is if I take a point minus a point. If I take a 1 point, I subtract another point from it. Yeah, you can get a point out of it. That's one way to look at it, this minus this point. But subtracting points doesn't really make that much sense unless you think of them in terms of vectors. So what they give me, if I take 1 point and I subtract another, it gives me the difference between the vectors, between the points rather. And that difference is a direction and an amount. That is a vector. So let me draw another example for you. 1, 2, 3, 4, 5. Right? Okay, so I'm going to draw an example here. So let's say I have the following operation. I'm going to do 4, 4, which is a point, minus -1, -1, which is a point. So I have a point -1 down there, and 1, 2, 3, 4, 1, 2, 3, 4, right about there. So I have these 2 points. I'm going to take 4, 4, subtract the other one. Let's see what the math gives us. Well, I subtract them element-wise, so 4 minus 1 is 5, and then 4 minus 1 is 5, so I get 5, 5. So if I draw the vector in here, I get +5, +5 direction. So if I think about it starting there, you can see that it actually spans the 2 points. What's really cool about this, it tells you the difference between them and the direction. So I get a vector, it tells me how far apart they are and what direction they're in. Okay. Now, the other thing I want to talk about is how do we convert a point to a vector? Okay. Well, they're kind of the same thing. If I have a point, I'm allowed to think of it as a vector because I just told you to convert points to a vector, I use subtraction. So if I have a point, I can just subtract the origin. So point minus 0, 0 is just going to be my point, right? I can just treat it like a vector. It's no big deal. But the difference is important. The difference, I should say this differently. The difference between a point and a vector really isn't how we use it. How we use the numbers, okay? So when you're doing some math or some operation and you're doing something that expects vectors or expects points, stop and think. Right. Are these points or are these vectors? And we'll come across a prime example of this a little later in the unit when we talk about triangles and the sides of triangles and whether they're points or whether they're vectors, okay? This is very easy to confuse. Okay, so I want to make that point. Okay, so another operation I'd like to talk about is Euclidean length. Now this should be old news to everybody. It's high school math. Euclidean length of a vector. It's just like a triangle math, right? It's just the length of the hypotenuse of a triangle. So this is also known as the L2 norm, if you're more mathy, or just a norm of some vector v. Okay, or we also use the notation like this. I know this looks like absolute value, but in vectors it means length of the vector. And the way you calculate is you take the square root of the vx squared, because it's my v vector, plus the vy squared, and so on and so forth for each component. So it's just like the hypotenuse of a triangle in high school. x squared plus y squared equals c squared. Take the square root to find c. It's no big deal. That's called Euclidean length, and you're probably going to use this. Another thing I'd like to introduce is this concept of what's called a normalized vector. Okay. Now, a normalized vector, all that it is a vector with length 1. So it's called the unit vector. So it's a vector in a given direction of length 1. Okay, and this should look familiar. So if I have, it's sometimes written like that with a hat on it. If I have a vector like v, I can normalize it by dividing it by the length of v. Right, and if I do that, then the length of the v hat is going to be 1. And sometimes this trips people up, but I think the intuition is not so bad. If we draw, think about this. I have some vector here, and let's say its length is 5. This here length is 5. If I take that vector and I divide both components, not erasing, I gotta fix this. If I divide both components, x and y, by 5, bam, and I know the length is 5, then this is going to be 1, 1, right there. And I have a new vector, right? Well, if this is 5, 5, it is. But my point was that if I divide the length by even points, the length of the new section is going to be length 1. And it works for any vector, no matter where it is. If I divide it into even pieces of how long it is, the new vector is of length 1. So I'm not sure if my diagram helped or not. You're welcome to just memorize the formula. So this is not to be confused with what we call a normal to a surface. And we'll learn about those a little bit later. So it's not to be confused with normal. The normalized vector is scaled to length 1. A normal to a surface is something completely different, and we'll learn about that when we do 3D stuff. It's basically, it's a vector that points straight up. Points straight. Let's fix that. It's a vector that points straight off of a surface. Did I say circus? I meant surface. Straight off a surface. So if I have a surface like this, here's my surface, and normal straight up. Surface is here, and normal is straight out. We'll learn more about those a little later. Okay. The last thing I'll mention before we take a break is that vertices in OpenGL are typically points, not vectors. This is actually really important. And let's go through an example here really quickly, where if I have a triangle, I'm going to draw a triangle. And I'm going to call this V1, this V2, and V3. If I have coordinates for these points, they're just points in space. They're not vectors between them. People often get that confused. However, I now know how to calculate these vectors. If I want this vector here that goes from this point to that one, I do V2 minus V1. If I want this vector here, I do V3 minus V2, and you guessed it, if I want that vector there, I do V1 minus V3. It's really easy. It's not hard. Okay, so let's take a break here, and then I'll come back and we'll learn a bit more about math. A good one.